Okay, so we're ready to talk about the phase changes. This is part 2 on the notes. I don't know, part 2, part 3, whatever it is. It's the next thing on phase changes here. So when we're talking about phase changes, the first thing we want to do is we want to look at the fact that when you have a change in phase, you're going to either have something that's exothermic or endothermic. Exothermic means it gives off the energy. It dumps the energy. It has to get rid of it. It doesn't mean we can feel heat coming off of it. Sometimes you can, sometimes you can't. Your hand is not the tool to use to determine if it's exothermic. Okay? If it's really obvious it's, on fire, yeah, we can tell that. But most things aren't going to be on fire, so we can't use just our hand and say, oh, it feels hot. It's not going to work like that at all. So you have to stick these into your brain. If the molecules have to slow down, that means they have to get rid of the energy, right? That means it's exothermic. If the molecules have to speed up to get to that, it means it's endothermic. You have to give it energy to speed it up. Yeah? Okay, so we have melting and freezing. Melting is endo, freezing is exo. Melting is endothermic because you're going from a solid where they're just vibrating into a liquid where they have a much greater range of motion. You have to give it heat, give it energy to do that. So we've got these things. Here what we were talking about, the last thing we wrote down, is that when you go from a solid to a liquid to a gas, if you go up solid to liquid to gas, it's endothermic, it requires energy. And what happens is you have a positive delta S, and this delta S is entropy. Okay? If you go back down the other way, we have a gas to liquid to solid. It has to dump the energy out. So you go from more chaotic, dump it, and you dump the energy out to where it becomes more ordered. And that means you have a negative delta S, entropy. Entropy, another word for entropy is chaos, disorder. Yeah? So if you think of it as disorder or chaos, then it makes more sense here. So we were talking now, then let's focus on that energy. And we're going to start talking about the different forms of energy that we use in here. And the first thing we talk about is heat of fusion. Heat of fusion is the amount of energy that must be put into a solid to melt it. So the heat of fusion, and when we say heat of, a lot of times instead of calling it heat of, they call it enthalpy or heat, capital E. So heat of fusion a lot of times is E, enthalpy, and enthalpy, if I can spell that, sorry, that's a Y. Enthalpy, and enthalpy, E, energy E, it's the same thing. Enthalpy is a specific type of energy. So enthalpy, and a lot of times what they call heat of fusion is E with, and it'll be spelled out fusion right here. Enthalpy of fusion, heat of fusion, energy of fusion. How much energy do you have to put into it to get it to melt? To get something to melt, again, to go from a solid to a liquid, that's endothermic. Now, I'm going to tell you another one. A lot of times they use H for enthalpy. So you're going to find some different letters that they use. It just depends on what it is they're talking about. So they can use, in general, they can use enthalpy. They can use E and they'll label it heat of fusion, or they'll use H. It just depends kind of on who's writing the questions. So they can do that. It's the same basic thing. So you're going to see different letters, and again, it depends on like who's writing the stuff down. A lot of times, I tend to see the H's a lot in the books that you have here, the Zoom doll books, the black AP chemistry books. So I like that. Yeah, delta just means change. So if I put a delta in front of that, delta E or delta H, that just indicates that we're changing it somehow. What's the change in energy? What's the amount of energy you added to it? So we can do that. Now, when I look at this S, we can also talk about S as entropy. So I'm kind of giving you guys this a little bit early, but I'm going to go ahead and put S Now, I just want you to kind of be aware of what's coming up, of kind of giving it to you a little bit at a time so you can say, oh yeah, this is not brand new. S is entropy. Okay, so let me be more specific with this. This is more of a broad topic when they call it E. It could be enthalpy, it could be entropy, it could be anything energy, could be that way. So a lot of times they'll just put E and call it generic. When they use the H and the S, then they're being really focused on it, and they're saying this is a particular type of energy we're talking about. So delta H, delta S, delta G, you're going to find those. So delta H is enthalpy usually, delta S is entropy, and when I say delta H, it's always heat. Entropy is always disorder. If there are more molecules, it's more chaotic. Think kindergartners. If you just have 2 of them, it's not so bad. But what happens when you have 15 of them? Yeah, the entropy, the disorder, the chaos increases, right? So more molecules means more disorder. If they're in a solid as compared to a gas, solids have less entropy than gases do. Again, gases are much more disordered. So you can get the disorder in that way. So as we increase up here, we have a positive delta S. That's why the positive, the entropy, the chaos increases. As we go back down from a gas down to a solid, the entropy is negative, it decreases. So when we talk about negatives and positives, one of the things they're going to ask you a lot about is, they might say, is delta S negative or positive? So when I put the delta in there, it means change in. You guys have had that in your math classes, right? Yes? Delta? No? No? Okay, so delta just means change in. So if we have delta S, it's the change in entropy. Did it change? Did it increase? Did it decrease? So you can have a negative or positive delta S. If you have enthalpy, did it increase the energy? Did the energy go into the system or did it leave the system? So you can have negative and positive in that way. Now, when we talk about this heat of fusion, we're always talking about changing states. So solid to liquid to gas, right? So heat of fusion is all about changing states. Solid to liquid. Usually it's between the solid and the liquid. That's typically what we talk about it. We can always, so I'm going to put a light X through that. I want it written down, but it's just going to change typically. Holy crap. So we want to change it from a solid to a liquid. That's heat of fusion. So when we deal with that, it's just a phase change is all it is. Yes, yes. Just so you know, you kind of keep it in mind there. So, more energy is required to change phase. If you have more energy that's required to change the phase, it means the substance has stronger IMFs. So, if more energy is required to change phases, it means the substance has stronger IMFs. And if not more, I'm going to put stronger out here. Stronger / more. Now, we can have heat of fusion, right? And we can also have, and I'm going to kind of, again, put it down here, we can have molar heat of fusion, which means that we're focused on 1 mole of a substance. Now, by dealing with the molar heat of fusion, what we can now do, since we've got moles, we can incorporate this into our stoichiometry. So molar heat of fusion is the amount of energy needed to melt 1 mole of a substance. So how much heat is required to melt 1 mole? If it's 10 kilojoules, then it's 10 kilojoules per mole. So now we can put that into our stoichiometry, because anything where you relate it to a mole can be used in your stoichiometry. And this is typically going to be in kilojoules per mole, is what it usually is. And again, if you want to put it in your stoichiometry, you can put the mole on top, the kilojoule on bottom, because they're equivalent. It's kind of like when you say 12 inches is equivalent to 1 foot. It doesn't matter if you put 12 inches on top or 1 foot on top. You can flip those around, right? They're equal to each other. It's like 1/1 or 5/5. Same way here, kilojoules per mole. If it's 10 kilojoules is required to melt 1 mole of a substance, 1 mole of a substance can be melted with 10 kilojoules of heat added. They're equivalent to each other, so you can flip it on top or bottom. Okay, we have heat of fusion. That's going from solid to liquid. That means we can also have heat of vaporization. And heat of vaporization is the amount of energy needed to change a liquid to a gas. Okay, so when we talk about heat of vaporization, again, it's the same basic thing. We're still talking about how much heat is required to change it from one phase to another. It's just that they're going to label it clearly for you guys. So it's not just going to be, hang on, where do I have it written up here? It's not just going to be E with a fusion word beside it. It can also be E with vaporization. Or in this case, a lot of times they'll put H of fusion or H of vaporization. Okay? So again, I'm showing you the H letter because it's going to pop up later on anyway. So it's just they're going to label it. So don't get freaked out because you see something that's got all this crap on it. That's just labeling it and telling you, hey, this is the energy we're talking about. This is what we're focused on right here. So the heat of vaporization, how much energy is needed to change the liquid to a gas? It is endothermic, right? Changing a liquid to a gas is endothermic. So it's an endothermic process. And if you look at this, is delta S positive or negative when you change a liquid to a gas? It's positive. So it's endothermic. It's a positive delta S. And really, when we talk about it, it's the energy needed to completely overcome the IMFs. Again, it's all about IMFs. The intermolecular forces. We know the strongest ones, and this is, they might, again, bring this up to you guys. We know that the strongest intermolecular forces are going to be in solids, but they're absolutely moving. I mean, they're absolutely non-moving, so we don't usually talk about them a whole lot. It's a given. It's one of those things that you understand. Well, yeah, they're so tightly put together. And it does have a little bit of an effect on the melting point, but really what it's all about is, when you talk about IMFs, it's all about when it's in solution, when it's in a liquid form. That's when we really notice the impacts compared to other like chemicals is what we have here. Okay, so again, this is going to be kilojoules per mole. So same kind of thing going on. We have kilojoules per mole. And the other thing we talk about when we talk about heat of vaporization is the vapor pressure, because the vapor pressure is going to have an impact on this too. Because now what we're doing is we're talking about gases. So changing from a liquid to a gas. Okay, so why do we have a different boiling point at sea level than we do in the mountains? You know it is, yeah. Why does water boil at 100 degrees at sea level and 97 or 96 in the mountains? Yeah, you know that, right? You've known that for a long time. The reason is vapor pressure. So the boiling point is when the vapor pressure equals the atmospheric pressure. When you reach that, when you get the vapor pressure equaling the atmospheric pressure, then a substance is going to boil, right? If the atmospheric pressure is lower, it takes less energy to reach that vapor pressure. The vapor pressure is, what's the pressure of the gas right above the liquid? Okay? Just right above the liquid, what's that pressure? That's the vapor pressure. Because you're always having stuff change into a vapor, a gas, and back and forth there. It's just natural way it happens. So when that vapor pressure right above the liquid equals the atmospheric pressure, it's going to boil. If you have less atmosphere, a lower atmospheric pressure, then it boils at a lower temperature. You don't have to put as much energy in it to get it to boil. When you're at sea level, you've got a lot more atmosphere, so it's going to take a lot more vapor pressure to equal the atmospheric pressure. Okay, so the vapor pressure is the pressure above a liquid. Again, just talking air pressure, right? Or whatever gas pressure. Pressure above a liquid caused by molecules that have escaped from the liquid into gas form. Just naturally, they're just naturally going to do that. If you look over that tank, now I have a little cover on it, a little plastic cover on it, but you look at all the moisture on the sides of the tank. I only put water down on the bottom of the tank. That means that water had to naturally change into a gaseous form without me adding heat to it. It had to change into gas form and then it condensed. It's constantly changing to gas and condensing, changing to gas and condensing. It's a constant process. There's a balance. There's an equilibrium there. I don't know if you can see, but I poured water on the sides of the tank just so I could see inside there a little bit better. So you can see where I poured it off, where it's come off. The other part where it hasn't poured off, it's just a constant process. At some point, you'll see the little drips coming down the side where it builds up enough water on the side that starts to drip back down. And so you have an equilibrium built up where you have water, even without me heating it, changes to a gas. The gas condenses back to a vapor, back to a liquid, and you've got this process, this cycle going on in that tank over there. So the pressure above a liquid is caused by the molecules that have escaped from the liquid into gas form. So if you have your tank or your beaker, you have, and you can have solid stuff in there too, but if you have the liquid stuff in here, there's going to be a vapor pressure right here just from that substance that's right there. Ignore the atmospheric pressure. The atmospheric pressure is there. Hang on. The atmospheric pressure is there, but this is just from molecules changing to a gas, and then the gas changes back to a liquid. There's an equilibrium, a balance there. Yes?
Will we be writing anything on the bottom?
No. Okay. So this is where this is the vapor pressure. Everything has that. If the vapor pressure equals the atmospheric pressure, it causes boiling. So when that vapor pressure, and again, we could get a barometer and measure that vapor pressure. It'd have to be a good tool, but we could do that. When the vapor pressure above the liquid equals the atmospheric pressure around it, it's going to boil. Now, this is something they're going to ask you about, and this is one of those conceptual things. You can't calculate it or anything like that. I've pushed a little bit of stuff to the side over here, made a little spot here. And I'm going to turn it sideways and write this. If there's a high vapor pressure, it means there's a lot of gas, there's a lot of the liquid that's changed to a gas. If there's a high vapor pressure, it means that the liquid evaporates easily. That means it's volatile. Okay? They're going to have some questions about that. If there's a high vapor pressure, that means that stuff changed to a gas easily, right? A volatile liquid changes to a gas easily. That's what that word volatile means. It changes to a gas easily. So think Paint. You've opened a can of paint, right? And you can smell it pretty quickly, right? It's volatile, it changes to a gas easily. The vapor pressure right above that is going to be pretty high. If it has a high vapor pressure, it means it reaches equivalent to the atmospheric pressure really easily, and that means it has a low boiling point. So high vapor pressure means a low boiling point. And that means low IMFs, or not very strong IMFs. Okay? So if it has a high vapor pressure, it means that it changes to a gas really easily. Changes to a gas really easily. If it changes to a gas easily, it means, oh, there aren't that many IMFs holding it together, right? So high vapor pressure means it's going to have a low boiling point and low IMFs. Think about that just a second. Say that to yourself over again and think about what that means. That's something that people get messed up on. It's when you read it, it's pretty simple to think of. To think, okay, yeah, I get that. But when you get this on the test, where you're going over this and all this crap is on there, and you're thinking, what? Okay, so you have to stop and think through. Okay, so high vapor pressure means it changes to a gas easily. There's a lot of pressure of that liquid that changed to a gas right there. If it changes to a gas easily, it means not very many IMFs, right? And it means if there's not very many IMFs, it means there's a low boiling point. It's easy to boil. The more IMFs there are, the higher the temperature it takes to boil it. Okay? So one more thing. So here I have two beakers here, and here's my liquid. Here we would have a high vapor pressure, and here we would have a low vapor pressure. Low vapor pressure means then that, hey, there must be a lot of IMFs because it's not changing to a gas very easily. Here? No, those are just dots. Yeah? Yeah. So here we have a high vapor pressure, so there are lots of gas molecules, lots of the liquid that's changed to gas in here. Here we have a low vapor pressure where there's not many of the molecules of liquid that change to a gas. And remember, pressure is just, how many times is it hitting the sides of the container? So more molecules means more pressure. Okay, I'm going to stop this one here.